Hello, everybody. Welcome to the latest, I can't remember what number we're on, virtual meeting of the Royal Met Soc. People are gathering in. I can see the attendee number going up quickly. So, hello, welcome. Say hello in the chat. Let us know where you're from. I shall say hello quickly. Hello from sunny Reading in this case. So there you go. Just about make that one in. So obviously we'll have Dr. Ben Pickering, who's a research fellow from the University of Leeds, giving our talk on the golden age of weather radar soon. If Anthony's made it in, he'll already recognise that term, which Ben may or may not notice. But I shall go on in a moment. So we're getting people sort of welcoming from rainy Toronto. So Daniel seems so far is clearly winning the longest range, unless this is a sort of local Toronto I don't know about. Right, so let's talk about the Met Society, and then I'll go into my weather summary while people start arriving. So first, Met Matters. So sign up to the Met Matters newsletter and enjoy your monthly newsletter of weather and climate stories, information of events, meetings, weather and climate. So participate in citizen science projects, which hopefully are increasingly important and so on in the science of meteorology. Hear from a variety of experts with guest blogs and so on, and discover the stories behind what's happening in the sky right now outside your window, which right now outside my window is blue. And those of you who can see my screen, I'm actually weirdly well lit tonight because there's this sun outside my window is actually in the right direction. Then the next thing to say is if you're currently a university student or received your highest degree in the past 7 years, we want to hear from you. So there's a £10 Amazon voucher for an hour of your time. So so what they want is to have a couple of virtual focus groups and thoughts about the publication in weather. So go have a look. Welcome to more people saying hello. So we've had Scotland. You don't quite get. We've had a few Scotlands, but we're not quite reached Toronto yet levels of beating the long distance. Obviously, you should become a member of the society if you aren't one already. Get your weather magazine delivered to your door, or these days probably in the modern world more online, but other discounts for conferences and meetings and for the other journals, and of course access to support grants and so on. So visit the website for membership. After Ben's talk, we'll have a Q&A session. So if while Ben's giving the talk, you write any questions in the chat, then Simon or I can mark them as questions, and then I'll ask them towards the end in our Q&A session. But you can continue adding them there. But if you do them as we go, then Simon and I can sometimes even try and flag a little in our little secret admin section, so I can help remember what slide numbers we were on. So that can be useful. Then also, I'm going to give my weather summary. So please ask questions in the chat. We won't flag those as questions, I don't think, but I'll try and answer them, because if we were in real life, this would be more of a discussion than anything else. So I'd like to maintain that still happening, really. For those of you who are new to Demio, and a lot of the names I recognise, but some I don't, so you're probably new to Demio or potentially new to Demio. So here's a few tips. It does tend to work better in Chrome or Firefox from my experience, or Safari if you're on a Mac. Edge is good, but doesn't seem perfect. But my experience, Chrome seems pretty much flawless. You can make your slides bigger with the expand button, and you can close the chat window to make it even larger if you need to. But obviously, you want to bring that chat back for sending us questions. So that potentially we could use polls, but we haven't got any set up for this talk, so let's ignore those. And move into the weather summary. We're getting so I can see Helen has asked if there's text captions will be available, but you heard nothing back. I believe when it goes onto YouTube, YouTube probably will automatically give you text captions. So when it's live, there wouldn't be subtitles, but I think when it goes on YouTube, there would be. I can't say I know how good they'd be, but that is probably my answer. Hello, John. Radar Met Man at Malvern. There's too many radar people in this meeting, I'm afraid, with Ben and I, and now then John, and probably Anthony is hiding in the background as well. Then the radar people are in good numbers. So continue. So onto the weather summary, and I'll talk about April 2021, where there was some fairly sort of well publicised. It was cold. There you go. Ben has answered that he's right. The captions will be on in the YouTube version. So hopefully the YouTube version will have captions for you, Helen. So hopefully that's helpful to you. Right, so it was well known. We all know it was cold in April, but there was another record that surprised me rather more that we'll come to. But let's look at the UK as a whole for April. And my standard charts that I've been using straight from the Met Office website, and fortunately managed to get these in time. So this was the mean temperature for the UK as a whole for April. And we can see that this April, the mean is cold at just below 6, about 5.8, that is. But probably most noticeably, it's the coldest since 1989. So cold for a long time, for the coldest for quite a long time in the mean. But it wasn't really the mean was very cold. It's not that special in comparison to the mean minimum, where it was really cold. So we only averaged just over freezing, really, and that was the third coldest going back to 1885 that this goes back to, and the coldest since the 1920s. So yeah, I'm sorry, Helen, for the. Hopefully, if you come back and watch the YouTube version, you'll be able to see it. You'll be able to hear it. Not much help for you though. Probably me telling you that isn't much help either, but good luck. Right, so where are we? So cold overnight minimums. I think we've all known this. So let's have a look at the rain as well. And it was very dry, and probably most of you know that. In fact, in Reading, for almost the entire month, I'd been commenting that it hadn't actually rained at all. We had 5.1 millimetres fairly early in April, but it was snow, not rain. And then we had a bit of rain right towards the end. So the UK as a whole was just a fraction over 20 millimetres. And again, you can see that was one of the driest on the record and for a long time. So then sunshine though, and I remember this sort of time last year thinking how amazing we'd had the sunniest April on record. Yeah, so the sunniest on record last year, and this year beat it by a very tiny amount. So we've had 2 Aprils in a row that have both been the record-breaking sunniest Aprils. And that's probably closely related, actually, to those really cold overnight minimums, of course. It's been clear, so that means radiative cooling is really very, really very strong. And so we've had a lot of cold. And we'll see in the Reading data as well that this sort of really followed into Reading too. So here's the maps of the temperatures. So I've got the mean max, mean, and mean minimum here. And you can see basically the important, and these are the anomalies to the 81 to 2010 values. And basically the important point here is blue, and really blue on the minimums. So just cold and basically cold universally across the whole country for those overnight minimums in particular. So that's the minimums. You can also see incredibly dry. The rainfall absolute amount, sort of the left plot here, it just shows you just how dry, and that we're basically in the bottom category for practically the whole of England and southern Scotland. And I don't think there's actually any blue at all on the map. So normally these maps, I always think the colour scales are a bit strange because it basically just means, oh look, there's the Scottish mountains in blue. Not this time. And you can see in the anomaly plot again that it's just been incredibly dry and absolutely nowhere blue. So nowhere at all is wetter than average. About average is as wet as it got. And these are very few and far between for that. Incredibly sunny. That probably doesn't surprise you, having had the sunniest on record for April. Really, the southeast has been the least sunny. So our region was the least sunny of all, and still talking sort of 20-30% up on what you'd expect. So a really sunny month as well. And again, nowhere even average for sunny, where everywhere in the whole UK was sunnier than average. And then the last one that I wouldn't normally show is the frosts. So days with air frost and days with ground frosts. And the first thing is I heard the statistic from one of the BBC weather presenters who told me that there had been a frost in Britain somewhere every single day of April, which doesn't normally happen, apparently. But you can see here just how many there were. You can see here that there's a lot of across the whole of England of both air frosts and ground frosts. So I've tried to do here air as the top one and ground as the bottom one, and the left two are the actual numbers and the right two are the anomalies. And the important point really is that the air frosts, for most of the country, the anomaly is between 5 and 10 extra days of air frost. And then, well, for instance, in the southeast, we're really on average for April would be just 2. So that's a massive, massive extra. And the ground frosts, where you'd expect somewhere around the region of 10 to 15 in this part of the world, we're having an extra 10 or so. So a huge amount. So we'll see where we are. So I've moved more locally and gone to look at our statistics for Reading. I have found out that I've been done by my own website that works these statistics out. So one of my records on here isn't actually true, but we'll come to that one. The important point really here is just how cold we were. All 3 temperatures are well below average, but particularly those overnight minimums. So in Reading, averaging 1.66 degrees C, which is 3.44 lower than you'd expect for April. For this, we're using the 1991 to 2020 averages from Reading for our data, and you can see nearly 3.5 degrees colder than average minimum temperature is a huge amount. And our rainfall, 13.4 millimeters, absolutely all of it fell in just 4 days. And 2 of those, they had 0.1 millimeters and 0.2 millimeters. So that was 72% less than we'd normally expect. Then the sunshine hours, 226, which was nowhere near as high as last year in Reading. But as you saw from the map, the UK, it was really Scotland and north of England was much, much sunnier than average. And that's where the UK record went from. But our temperatures particularly were what was really record breaking in Reading. So I think I've commented in the last few months, I'd like some nice records. And I think we can claim some nice records here. So the lowest April mean temperature for T-min since 1924. So that's a really long time, nearly 100 years. The Reading record starts in 1908 for temperatures. So a long record, and that's one of the very coldest we've had. It was actually the lowest T-mean since 1986. Unfortunately, I was alive, but Simon wasn't. So we can safely say for a long time. And even T-max was the coldest since the year 2000. So all of the temperatures were cold compared for the last 20 years. Then the frosts. So we had 11 air frosts, which was the most air frosts in an April since 1917. So even longer, and 9 more than we get than our average, which is actually it's a little bit more than 9 because our average is 1.9 air frosts for an April, and then 25 ground frosts. So almost every day had a ground frost, and we averaged 15. So again, much more than before. Our ground frost record isn't anywhere near as long. I can't remember, but I think it was the most ground frosts on the record. But it's not a particularly long record, so I didn't actually go and check for absolutely certain myself. And unfortunately, my last stat on this one isn't true. The only 2 rain days, we actually clocked a 3rd one on the last day of the month, where just by reaching 0.2 millimeters. So we weren't the equal least on the entire record because we had 3 in the end. So one of our 2 more with very small amounts actually turned out to be 1 more with a small amount and 3 real ones. Yeah, and as Simon has pointed out in the chat, we had a minus 11.2 grass minimum, and actually that was pretty right home worthy even in winter. We do get them that cold, but it was very unusual to be anywhere near that cold for April. It's spectacularly low grass minimums really throughout the month. And so my last slide in my weather summary is actually of my girlfriend, who some of you may have been able to spot behind me until she just went out, who works for the Royal Meteorological Society. So one of her levels of boss we shall consider managed to get the quote. And I know that she's been getting a lot of inquiries and so on. The Royal Horticultural Society. What did I say? Did I say something else, Simon? So Guy Barter, he did the considerable damage has been experienced in many gardens, with flowers, particularly camellias and magnolias, being scorched, with cherry, plum and pear blossom injured, so the fruit crop will be reduced. And I can safely say for my garden, I have two cherry trees in my garden. Both of them were in absolutely full blossom before the first of those really hard April frosts, and it has not done my cherry tree any good at all. I appear to have almost no cherries coming, so it's not done my cherry crop any good at all. And I imagine that could be a big problem for proper fruit crop growers as well. And I know that the RHS have had a lot of inquiries and questions of basically badly frost damaged plants, so it's going to be a serious problem for this year. Looks like I've managed to answer the only question that was asked, which was the fact that I can't tell the difference between the word horticultural and meteorological on my own slides, which is typical of me, I think. So I think that means it will be time to move on to Ben. And if there's any more quick question, I shall read out Ben's bio. So our sort of main talk this evening is going to be on the golden age of weather radar. Here you go. And our speaker is Dr. Ben Pickering of the university, who's a research fellow at the University of Leeds, studying observation techniques for atmospheric science. So, sounding very exciting there, Ben. I can see you've done an excellent job in your background of having one of those observational techniques on the wall. Currently, Ben's researching rainfall retrievals from satellites using machine learning techniques as part of the African SWIFT project. Prior to this, Ben completed a PhD on ground-based precipitation radar, and specifically, there's another word I can never say, looked at verification techniques for precipitation-type products. Outside of academia, he's an avid storm chaser and a UAS drone pilot, which I fear makes you very cool amongst the young folk. That I definitely no longer count myself as. And you like to create videos of your travels around the world when permitted, which obviously isn't now. So, Dr. Ben, tell us about the wonders of the golden age of weather radar.
All right. Thank you very much, Rob, for that amazing introduction. So, yeah, good evening, everyone. Thank you for joining me tonight. I'm going to speak for about 45 minutes on weather radar, although Rob has advised me that there's no real time limit, which is a pretty dangerous thing to tell an academic, I think. So just before we get started, I should mention that obviously we don't work in isolation. There are many different people who contributed to me arriving in this location at this particular time. I particularly like to thank the first professor who taught me radar, which was Professor Mike Biggerstaff at Oklahoma University, Professor Chris Bird, Dr. Ryan Neely, my PhD supervisor, and a whole host of other people who have contributed over the years to these set of slides and to my development. So just to set the scene, here's what we care about, really, is a standard wave. And if you ask a PhD student studying weather radar, they might tell you, if you ask them what this represents, they might give you a bit of a sarcastic answer and tell you that it represents their ambition, their hopes and dreams, or their greatest enemy. Whereas an actual legitimate physicist might tell you that the important things here are amplitude, frequency, phase, and time encoding. And while I am recently a PhD student, so I still consider myself mostly in the top segment here, I am starting to work my way towards the bottom segment. And this talk is going to form part of that as well. So I'll just kick things off with a nice little video, just giving you literally the most basic way of describing weather radar. So hopefully you can all see this. We've got precipitation and we have radar, and we send out a very concentrated pulse of high energy electromagnetic radiation, and immediately the radar is put into listening mode. So it sounds like this tiny little pulse, very high energy, and it goes out to the precipitation. And depending on the amount of precipitation there, you'll get some backscatter, and the radar is now listening for what is coming back. And so you get the amount of energy coming back, and you can also use the speed of light and the time it took for that pulse of energy to go out and back to determine how far away it is. So that's radio detection and ranging. So going back to the slides, I'll just give you an overview of what we're going to cover this evening. I'll split this up into 4 different chapters, if you will. First of all, a brief history of radar generally, so not specifically for weather, just radar for any use case. And then specifically drilling in onto how weather radar works and some specific elements that are useful for meteorology. And then I'll talk about the state of weather radar today. We recently had an upgrade in the UK, so that's very exciting. And then I'll talk a little bit about my opinion on the future of weather radar. And this will all come together and then sort of tie in as to why I think we're in the golden age of weather radar. And if this isn't exciting enough for you, then we also have some bonus content. We've got some cool facts scattered throughout the talk. There's also some poetry, some original animation, one of which you've just seen, sheep, and also drones as well. So if that's not enough for you, then I don't know what would be. So just to get us all started, I'll talk about radar in general. So we need the radio before we can get the DAR. So first of all, way back in the 1830s, almost 200 years ago now, this guy called Faraday came along and performed some physical experiments on electricity and magnetism and how they interacted with each other. Faraday didn't have many qualifications, so the results of his experiments were largely, ignored because he didn't have the mathematical proofs to show what was going on. It was just the behaviors within his experiments. So then a couple of decades later, James Clerk Maxwell came along and did have the mathematical abilities to solve the equations which needed to be resolved from the experiments of Faraday, which in itself then theorized the existence of radio waves for the first time. Then a couple of decades after that, Heinrich Hertz came along and proved physically that radio waves could be sent through the air between 2 charged metallic jars, and showing that this could be a form of communication over the air wirelessly. And then just a decade after that, so it's speeding up here, a person called Marconi came along and was an inventor and used this scientific discovery and put it to practical use in the invention of radio communication. And this was initially used to stop ships colliding with each other in fog. And the first interesting fact of this talk is that if you go back through PhD supervisors, so my PhD supervisor and his PhD supervisor and so on, Heinrich Hertz is actually the 7th PhD supervisor back. So that would be my great grand supervisor, to be specific. And I put et al. Here as well, just to make the point that all these people get the credit for it, but of course at the time there's always other people working on it, and other people even within the teams here. So we're now moving into the 20th century, early 20th century. Radio communication is getting more common, it's being more widespread, people are using it for different applications, and we are starting to approach the Second World War. And now some rumors were coming out of Central Europe that the Germans had this piece of technology called a death ray, which may sound rather silly to us today, but at the time it was quite a concern for the British government. So the idea here is that, or the propaganda that was put out at the time, is that you could concentrate a radio waves with amount of energy in such a way that you could kill someone from 6 miles or 10 kilometers away. So this is obviously a grave concern. No one really knew if this could be done or not. So the British government tasked this person called Robert Watson Watt to calculate whether this was feasible or not. And I'll just tell you a bit about Sir Robert Watson Watt to begin with. As a Scottish-born radio engineer who actually worked at the Met Office from 1916. So it just so happens that the person who invented radar in general was also a meteorologist. And early on in his career, before the start of the Second World War and the invention of radar, Robert Watson Watt had actually worked on this thing called radiotelegraphic atmospherics, which are emissions of electromagnetic energy caused by lightning strikes. So you can use this information with triangulation to determine where lightning strikes are coming from. This was intended to warn pilots. And there's a paper here which is still available today through the Royal Meteorological Society, which first described this. And these are now called spherics, as a shorter term to describe this phenomenon. And another fun fact is that Sir Robert Watson Watt was a Royal Meteorological Society fellow by 1915 and was actually the president of the Royal Meteorological Society for a couple of years around 1950, the society through which I am talking to you today. So this is the problem that was posed to Sir Robert Watson Watt, and I'm going to pose it to you as well, so you can use the chat function here on Demio and give me your answer. The question was, how much energy would be needed to create one of these supposed death rays in order to stop a sheep at 30 meters range? So you've got this angry sheep shown here, it's charging towards you, and you just got an antenna and some energy, and you need to try and stop this sheep. I'll make it a bit easier here and put it in terms that you might be able to grasp more. A general household microwave is about 1 kilowatt. So how many household microwaves do you think you would need to stop this sheep at 30 meters distance away from you? If you were firing all the energy from these microwaves at this sheep, how many microwave ovens would you need? Any guesses in the chat? 10,000, 500. Pretty good guesses. Any more? 10,000. All right, I'm just going to say it. So you actually need 5 million microwaves, equivalent of energy, in order to stop a sheep at that amount of range. So it was immediately obvious to Sir Robert Watson Watt that this was never going to be feasible. You'd never be able to create this so-called death ray. And it seemed obvious to us today, but at the time, it was a bit of a concern. So yeah, that's 5 gigawatts of energy, and that's roughly an eighth of the UK's power demand in 2019, not in 1935. In fact, 1935 was the year when the national grid was first created. So certainly it was not feasible at all to do that. So your sheep's pretty happy. However, at the same time, while doing these calculations, they also did, someone in Robert Watson Watt's team did a back of the envelope calculation, and we believe it actually was on the back of an envelope, showing that if you sent out a pulse of electromagnetic energy, an aircraft, the typical aircraft at the time, would reflect back enough energy to be able to detect it and see the aircraft. And this was estimated to be about 200 milliamps. That's compared to a FM radio, standard FM radio, which receives about 2 milliamps in standard usage. So 100 times greater than an FM radio's antenna is able to receive. And often with different inventions, we don't really know exactly where it came from, but here with radar, we have this actual letter sent to the British government, and we can definitively say that this was the invention of radar. And it's quite interesting, actually. So Robert Watson Watt says, it turns out so favorably that I'm still nervous as to whether we have not got a power of 10 wrong, but even that would not be fatal. So the British government were very pleased with this and thought this would be a great invention to have for the any military uses that they might need in the coming years. And so Robert Watson Watt's team were given £10,000, which equivalent today is around the amount of a standard academic grant. And then it took 2 weeks for them to get all this money, or to send a letter to the government, get the funding from the government, and then set up a demonstration experiment. So this is a very rapid chain of events, which I'm sure many academics today would be very jealous of. So yes, on the 26th of February 1935, the so-called Daventry experiment occurred in Northamptonshire. And this is where they set up some antenna in a field, put some electronics in the back of a van, and they got a RAF Hayford bomber to fly from a BBC transmission tower. So they used the BBC transmission tower, cancelled out the signal that was being transmitted there, and were able to track the aircraft from miles away. And they said they could watch it coming from miles away. So this was the first successful demonstration of radio detection and ranging as well. And in 2010, I believe it was, a group of people, sorry, it was 2000, it was some anniversary recently of this event. And so a group of people got together and recreated the experiment, and they painted this van in the exact style that it was at the time that they got from photos and other evidence. So this is essentially a color photograph equivalent of what it would have looked like on that day when they first invented radar. So this was such an immediate success that the British government put it immediately to use. And so by 1939, only 4 years later, there were 20 towers up around the UK, which were used to detect aircraft. This grew to over 50 by the end of the war. And this was a network called Chain Home. They just had sort of they didn't have any direction to begin with from the radar. So they had to use triangulation and a chain of command, and it was quite complex how they did this. And there's actually still one tower up today. You can go and see it somewhere in Essex, location written there on the screen. So this was determined as a very key aspect of World War II for the UK. We only had about 600 aircraft versus the German Luftwaffe, which had around 3,000 aircraft. And the ability for us to detect and scramble aircraft with some warning of approaching enemy aircraft was determined to be one of the most critical things that determined the outcome of the Second World War. And actually, the funny side fact again is that the Germans actually sent a blimp along the East Coast early on in the war, and they were checking to see whether these towers were actually doing anything, and they determined that they weren't working. It was just like a propaganda sort of setup, and they basically decided not to attack these towers for many years throughout the war. And what happened was they set their equipment to the wrong frequency, so they couldn't see that the towers were actually emitting any radiation, and that was a fatal mistake that they made. And then just to give you a little bit of wrap up on this part of the talk. So Robert Watson-Watt later moved to Canada after retirement, and was one day driving down a road and was caught speeding by a police officer. And when he was pulled over and asked how the police officer knew the speed that Robert was going, the police officer pulled out a radar gun. And to that, Robert Watson-Watt said, "If I'd known what you were going to do with it, I wouldn't have invented it." And then on top of that, there's actually a poem which is allegedly written by Sir Robert Watson-Watt, which I'll read for you now. "Pity Sir Robert Watson-Watt, strange target of this radar plot, and thus with others I can mention, the victim of his own invention. His magical all-seeing eye enabled cloud-bound planes to fly, but now by some ironic twist, it spots the speeding motorist, and bites, no doubt, with legal wit, the hand that once created it." So I thought that was a pretty cool thing to do, and kind of just shows you the character, Sir Robert Watson-Watt. All right, so that's the history of radar itself. Now I'm going to move on to talk about weather radar specifically, and I'm going to do this by taking you through the journey that a single pulse of energy goes through from creation to emission, receiving, and interpretation. So we start off with constant stream of electricity coming into the radar. We need to build an electronic pulse. So we use Fourier transforms, modulators, and that kind of thing to generate the pulse itself. This then goes through the magnetron, which turns the electrical energy into electromagnetic energy. And this invention, actually, the klystron magnetron, has not changed since the Second World War. This was created or invented by someone in Sir Robert Watson-Watt's group, and it enabled sufficient energy at the right wavelength in a small enough device that you could mount radars on aircraft. And so this was absolutely critical in the late stage of the war. And it was placed inside a painted black box on the aircraft. And so when if the aircraft was going down or had to land in enemy territory, it would self-destruct, or the pilot would instruct it to self-destruct. And this is where the term the black box comes from, which is actually quite funny, because when we're operationally using radars, we often say, especially mobile radars on field campaigns, we often say that the magnetron's a bit of a black box because it can behave a bit strangely and drift over time with different, it tends to shift its frequency over time. You don't really know what it's doing, and you have to sort of just twizzle this little thing to get it to work again. So I thought it was quite funny. Next, the electromagnetic energy, or the pulse, needs to go, you need to move it around the radar and get it to the right place. So it has to go through this waveguide, which is a very precision engineered size in order to keep the wavelength at its set frequency and to not diminish the energy too much as it's being moved around. And these are very expensive, so you don't want these to break. And then that's fed into a parabolic dish, which focuses the beam. So it's not just going off in all directions. We're able to get a nice focused beam, and we can steer that around and look in different directions. So don't worry about the title. I'm not actually going to show you equations here. That's for later on. I'm just going to go through now emitting the pulse, how it interacts with rainfall, and then how it is received back. So the animation that I showed at the beginning, but in more detail. So we've got the energy being emitted, which would just be in all directions, but we've concentrated it into a certain direction, and that goes out and expands as it goes. So its power diminishes as it goes away from the radar. We need to take that into account. And it's going to intercept some object, I guess one raindrop, which is the red dot on the slides here. And then what happens to that energy as it intercepts that single raindrop depends on a few different things. So obviously you've got the cross-section of this beam, and your particle is not going to fill the whole beam. So you need to know what ratio, looking from the side, what cross-section of your object, this raindrop, how much of that fills the beam. It also depends on the shape, the orientation, and actually even the materials. So liquid water is different to ice in terms of how the energy interacts. Some energy will be lost through absorption as the beam travels through the atmosphere. And then the third thing is the way the energy scatters is extremely dependent upon the ratio of the wavelength that you've chosen for your radar and the size of the object which it's interpreting. So there's three regimes that can happen with this: Rayleigh scattering, Mie scattering, and optical scattering in the lilac-y blue thing on the bottom left there. So if the particle is really small, you'll get pretty much equal, compared to the frequency or the wavelength of the radar, you'll get quite equal energy coming out from all directions when the pulse intercepts it. But with Mie scattering, and definitely with optical scattering, you get more forward. And really what we want is more energy to come back to the radar so we can send out less of it or get a better signal. So here's just a plot showing why we want to be in the Rayleigh regime as well. It's not just the amount of power coming back, it's more, but you see it's almost a straight line in the Rayleigh regime. So the size of the object determines how much energy comes back in a fairly linear way. Whereas if you go into the Mie or the optical regimes, you can have an object of a certain size, and it could have many different power returns. So you couldn't really accurately tell what the size of the object was. So then once you've got your Rayleigh scattering occurring at the particle, that then obviously comes back to the radar. It dissipates again once it's going out. So after all of these processes have happened, if you compare the amount of energy you send out from the radar to the amount of energy that's received back, it can be 10 to the power of 10, so 10 with 10 more zeros, times less powerful when it gets back to the radar. So when you receive and when you listen with a radar, when you first send out the pulse, it's very energetic and it's very high amounts of power. But then when it's listening, it switches and it's very sensitive. All the electronics inside are very sensitive. So if you were to hold up a big metal sheet in front of a radar and it just immediately blasted the power back into the radar, you'd probably fry most of your electronics inside there. That would be bad. I'm obviously skipping over a lot of different things here. Many other factors can occur in this whole process. You can imagine how complicated it would be. If you are interested in this more, I can recommend this book, which helped me a lot, by Frederick Fabry. Yeah, that's a really good book, so recommend that. Right now, we want to turn the amount of power that we've got received back from the radar into some kind of precipitation rate, ideally. We've got a horizontally polarized beam because, yes, I noticed a comment about accurately drawing raindrops. This is what raindrops look like, not the traditional teardrop shape that you would normally see. They hamburger buns, they flatten out as they get larger. So it's good to have a horizontally polarized beam because you're going to get more energy back. There's going to be more of a signal that the raindrops have gotten wider because they're bigger. You only get the amount of power back. So essentially all you could do is use that for, I'll tell you later on, there's some other things we can do, but essentially you are summing up the sixth power of the diameter of these raindrops. But the problem is that if you have a lot of very small drops, they can have the same amount of power return as a few large drops. And that's the real problem, really. Also, in this case, you don't know the precipitation type. You have to just assume that it's liquid in most cases. So yeah, we're trying to turn the amount of power coming back, which is this Z factor, radar reflectivity factor on the left-hand side. And then what we want is rainfall rate, which is the sum of the size of all the raindrops cubed, the volume of the raindrops. And the problem is there's no mathematical way to actually equate these two because you can have multiple instances like small raindrops or large raindrops where they have the same amount of power returning, and that's a problem. However, in 1948, Marshall and Palmer, in this very well-cited and very famous paper, showed that as rain rate increases, the distribution of small drops and large drops actually behaves in a fairly predictable way. So this is an estimation; it's not an exact, mathematical way to do it. But we have to use this, and essentially allows you to relate Z to R in an approximate way. And this is how we all, how most countries now turn their radar measurements into rainfall rate. So it's just very simple, number multiplied by that raised to a power. So yeah, and there are so many of these ZR relationships now for different climates, different types of precipitation, like storms versus frontal. Different climates, just loads and loads of, probably hundreds of different ZR rates. Many debates over which one's the best one. So just to round off this section, I'm going to read a quote from this book that I recommended before, just to summarize like radar today and how it's used. Radar offers the forecasters what is generally the best opportunity to detect rapidly developing storms, and also the last one to evaluate whether the weather evolves as expected or not. So just highlighting there how important radar is in general for meteorology. So I'm just going to take a little pause here, and I'm going to talk a bit more about weather radar today, the upgrade that we've recently had in the UK specifically, and that is for dual polarization and what that actually means. So just to give a timeline, where are we in the whole meteorological side of this? I'm going to show this timeline. On the top is kind of like research elements that occurred. The middle is USA stuff, and then the bottom two there are UK things. So in 1940 around 1940 was the first realization that you're not just seeing aircraft on radar, you are also seeing precipitation echoes as well. This was over the English Channel. The USA were actually first to develop a proper network of radars and use it for forecasting, for observations in real time. Around 1965 is when dual pole variables were first derived. I'll get onto that in a second. And then around the 80s was when the first Met Office radar and then the network was first developed. In the late 1980s, 1988 specifically, the USA radars added Doppler velocity, which I won't really cover much in this talk, but you can get winds from a radar as well. And then around the turn of the century, around the turn of the millennium, in 2000 or just before, we first developed hydrometeor classification algorithms, which is now getting onto my PhD work, and I'll explain that in a second. So the USA added this dual pole radar grade around 2010, and the Met Office have just recently finished in 2017 the UK's upgrade to dual polarization, and a few other countries have done it as well. So now you're probably wondering, what is dual pole and what are hydrometeor classification algorithms, and why did you do a PhD on it? So I'll just first say the UK radar network, which has recently been upgraded to dual-pol, has 15 radars within the UK. These are all C-band, so 5.6 gigahertz frequency, and we get quite good coverage here. You probably know it's 5 minutes and less than 1 kilometer along the actual individual radar beams themselves. And we have 5 different heights as well, which are used to sort of quality control and get the best precipitation rate for the public. So the Met Office just completed this dual polarization upgrade in December 2017, and it took 5 years in total. So it was a big upgrade. They're actually developing, they developed the hardware in-house for these radars. So that was quite a good aspect of it. Right, so dual polarization, what is that? So I mentioned before that you would traditionally have just a single polarization. You'd want the horizontal so that you get the width of the raindrops, because that's more of a signal of the rain rate than the height of the raindrops. However, if we have both, if we have a vertically polarized beam and a vertically polarized beam, we can do a few different things. So this table on the bottom left is just showing you that you can emit in one polarization and listen in the other. So you could do vertical out and vertical back. You could do vertical out but listen for horizontal coming back, or any other combination of those things. So you get 4 things out. And then from this, there were, in the 1960s, there were a bunch of variables derived from dual polarization measurements. And I'm going to go through each one of these in turn, and then I've got another sort of question for the audience after that as well. So first of all, differential reflectivity. This is literally the ratio of the horizontal to the vertical amount of power that you're getting back, and then you take a logarithm of it. So if your particle is spherical, like a hailstone might be, then your ZDR is going to be near 0 because your ratio will be 1, and then if you take the log of it, it's 0. Raindrops flatten out as they get larger, so you're going to have your ZDR greater than 0. And then sometimes you can get particles in the atmosphere which are more vertical than they are horizontal. So snowflakes or individual ice crystals can sometimes be tall, and that would have a ZDR of less than 0. And then I'm showing you this thing in the bottom left, the very colorful graphic, which shows that for different precipitation types, there are some sort of general values that these will have, as you can see through the pictures in the top right. So I'll get onto it, but you can start to build up a picture of what the precipitation type might be based on all these different measurements. So next up is correlation coefficient. This is literally the equivalent of the R-squared value in statistics, if you've ever come across that. It's literally saying how similar are the particles within the radar beam. So if they're all identical, like drizzle, it's going to be very close to 1. And if they're all different, different sizes, if you had hail with rain, you'd get a value less than 1. You can never go below 0. If you get, for example, in America, you can get tornado debris. The correlation drops massively because tornado debris, everything's a different size and shape. So that is used as a good indicator to confirm that there was a tornado causing damage on the ground. And again, I should say, we can tell precipitation type a little bit from this. You see they're all overlapping, but we're building it up. Next is specific differential phase. So when the beam goes through a raindrop, because it's changing its medium, the speed of light changes, some energy is absorbed by the rain as it progresses further away from the radar, and the phase will be shifted a bit as well because it's slowed down going through the raindrop. And so you can use this to show how you can use it to say it's equivalent. It's kind of similar to ZDR, where you've got sort of a horizontal and a vertical aspect to it, but it's not weighted in the same way, so it is slightly different. And yes, there's a lovely plot on the bottom right here from our very own Rob Thompson, which I'm sure he remembers creating, showing attenuation. So you see, in some cases, if the precipitation is heavy enough, all the energy can be absorbed, and you get this weird shadow behind a storm where you would expect rain to be, but the radar can't see it because there's no energy propagating through the storm. Okay, so then the final one is linear depolarization ratio, and this is quite unique to the UK, operationally speaking. Not many other countries have this. Got this amazing animation created in the top right, showing why you would do this. So this is a case where you send out energy in the horizontal polarization and listen back in the vertical. Why you would do this is that if your objects are spinning, hail is a very good example of this. What it can do is it can actually flip the polarization. So you'll send energy out in one polarization, and then because it's spinning, it will backscatter in some of the energy in the other polarization, if that makes sense. So yeah, this can be quite useful for hail. Again, in the bottom left, you see that there's different values of this LDR for different precipitation types. So hopefully you're starting to see that these colorful plots on the bottom left are conveying information. On their own, they're not that useful, but if you combine them together, you can do something cool with it. So I'm going to go back to the slides. Okay, so this is the question for the audience. So I'm now showing you all these colorful plots again. I've given you values of these different dual parametric variables indicated by the red vertical line. And I want you to tell me what is the precipitation type that's being observed here. Gareth got it straight away with snow. So if this was in person, I would then pick on Gareth to explain the answers, but unfortunately I can't do that. So yeah, I'll just go through each one. So the first one, you can see it's not helpful at all, ZDR, because it covers literally everything. It doesn't tell us anything. But then when you look at KDP on the top right, you see that the value can only really be ice crystals or snow. And then if you combine the other information as well, you'll see that it can't be ice crystals, so it must be snow. And what you've just done in your head there is known as fuzzy logic. So you combine together different bits of information. If you did this in a probabilistic sense as well, that's more like fuzzy logic. And so, yeah, in this case, snow is 4 out of 4. Clutter is also 4 out of 4, but we have other ways of dealing with clutter. So, yeah. So this then comes on to my PhD work, my very small contribution to science. These kind of products, they're quite hard to verify because you usually need aircraft to go up inside these clouds and measure the precipitation. And that's very expensive and we don't get much data of it. So it's typically just like a handful of cases that someone's picked out and looked at with their eyes rather than like a big data approach to it. And so what I decided to do in my PhD was to get a version of this product which is at ground level. So it's using temperature to get it to what the precipitation type should be at the ground. We then got a bit more data to verify those kind of products, but we still didn't have enough and it wasn't high quality enough. So what I did was deployed this network of laser precipitation instruments, and they can individually detect, individual hydrometeor, individual precipitation coming down. So we can see individual raindrops, snowflakes. We think we measured tens of millions of individual bits of precipitation over the project. And what it does is it measures the fall speed and the diameter, which I can explain in the question area if someone cares. With that information combined, you can infer what the precipitation type should be because there's different relationships for precipitation for fall speed and diameter. And then one of them was up in Scotland and had a bit of a hard time. It gave us some good measurements, but yeah, it definitely struggled. This is completely solar powered, and it's actually still functioning in all this ice when this photo was taken. It wasn't giving us good data, but it was still on and running, which when you consider it's being run by a solar panel and a little turbine, I thought that was quite impressive. So yeah, I had to go up there and chisel off all the ice. Very dramatic. And then I also included some crowdsourced observations from Twitter and other places to do some hail verification because we still didn't have enough hail data to verify this kind of product. So yeah, I'll stop talking about that now, but it did result in some suggestions for improvements to this product. So that was my PhD in a nutshell. All right, I'm going to wrap up now and talk about what I think the future of weather radar is and why we're in the golden age of it. And I'm going to cover this in 4 sections and in 2 different topic streams. So the first 2 are more about like the hardware of the radar, and then the last 2 are more about like the use and the application of radar. And there's probably many more, and these are biased because of my experience as to why I'm showing you these 4 specifically, but I think they're quite important. So, all right, so going back to our timeline again, radars originally, when they were first used as weather radars, you would just get these sort of fuzzy images, not the precision that we have today. You couldn't really animate them at all. You'd have to draw over them on a plastic, your overhead projector that you had at school, to get some idea of where they were moving. Moving forward in time, we started to get digital displays and color displays, and you could do some animation, but it was pretty slow. It wasn't great. We didn't have amazing computers. This is actually a nice line of storms in Norman, Oklahoma in 1985. And then if you come to today, this is originally a video, but I haven't got the video for you now. If you've been to America and used the radar apps there, you can whiz through all the dual polarimetric variables that I described before. You can go up different heights in the atmosphere, different tilts. You can animate it super easily and with like a long timeline as well. It's got very high resolution. You can get the raw data. You can get it to show you everything, no quality control. You can draw over it. You can zoom in, measure distances. It's just a whole nother level. And what comes with this is that the expectation or the demands from the users of these products increases as well, and they expect more precision. You can't just increase the resolution. You also need to, have evidence that it's actually precise enough to be used at this resolution as well, and things like that. So more demands are increasing, shall we say, as we improve radar. And so if you just go back to the original explanation I had of radar, the energy goes out, backscatters back to the radar. You can have a pretty simple equation to describe that. But then as you get to more precise demands for the measurement, you can basically add as many terms as you want to the radar equation, right? You could probably add like an infinite number of terms, processes that happen in the atmosphere, things going on with the hardware inside the radar itself. All the components would have an effect on what's going on, and you would need to calibrate for all of those. So, and then, these are all the hardware things that are going on. So, the more you think about it, the more problems you find to fix or calibrate against with your radar. Well, another thing, I lied before when I said radar beams look like this. That is not true. It's actually more like, because it's a beam of energy, and it's a wave. So you can imagine it more like if the radar energy is coming towards you, you can imagine it more like a drop in water. And so the wave would be propagating up in this diagram. And then if you took a cross section of that, you can kind of imagine, if you took a slice through that, it would look a bit like this. This is actually a slice of a radar beam and the amount of power coming from different directions. So if you rotate this back into a 3D beam, it really kind of looks more like this in some cases. So it's not simple at all. We need to calibrate against this as well. So I did do a little side project during my PhD working on this, which is why I'm showing it to you. Traditionally, to get this kind of pattern from the radar, the beam pattern, you would erect a mast if you had planning permission to do so, put a known reflector on, which is this 2,500 quid Lunsberg lens, I think they call it, on top of this mast, or some standard reflector, and you'd point your radar at it and scan it. Problem is, it's quite hard to get these towers to be very high. There's often, the actual structure of the tower itself is metal, not great for trying to calibrate a radar. And in the lower right here, you can see an example of this kind of calibration that you get. And it's okay in the top half, but if you had to assume it was the same all the way around, but there are a lot of other things going on because it's near the ground. So it's not super ideal. So we had this idea that we wanted to test out because we saw some people in France do it, where we could use a UAV to hang a sphere or a known transmitter below a UAV. And then we also had a GPS unit below that just as a counterweight. And then we could use the 2 GPS from the lower one and the UAV to know exactly where this sphere was in the middle. And it's super easy to, once you've set it all up properly, it's quite quick to get this UAV up compared to erecting a mast. Some places you can't erect a mast on field campaigns. And the idea is we do the scan around with the radar again. And we just wanted to see how feasible this was, how easy to use it would be, and answer a load of like logistics questions about it. So we did this at Chilwell. Oh, and also, you know, it's proper science when the main piece of kit, the sphere itself, was bought off Amazon for about 20 quid, a garden ornament sphere. But because it's, I think this was some type, was it stainless steel? It was either stainless steel, yeah, stainless steel. So it was a good enough object that we could use. Obviously, we were doing this properly, we'd need a very expensive calibrated object, but for an initial test, it was good enough. Lots of fun. So then I've got a video to show you of this. This was actually the last time I was out doing field work, and coronavirus was kicking off when this was when I was out here doing this. So I pretty much came from this field work home, and I haven't left since. So yeah, here's the ignore the very badly tied string. Yeah, and theoretically we can fix the motion of the sphere by using the 2 GPS units. So yeah, the radar, it's not the big radar there, it's a tiny little one in the car park, which I can't point to because I don't have a mouse to show you. But yeah, and that's our GPS. So yeah, that's a sort of summary of what we did there. I can show you some results from that. Yeah, so we get quite a clean signal from it. That's the takeaway message. And we also didn't see the drone. We wanted to see if that would show up, because that would be bad for what we're doing. But either the materials within the drone or the profile of it from the side, it just wasn't enough to give us a real strong signal of it. So that's good. Work is ongoing with this. Yeah, it was just a preliminary piece of work. So then next up on hardware side of things, we sorted out calibration with drones. The real major thing which is going to change going forward with weather radar is a technology called phased array. So for the last 100 years, we've had radars that are parabolic dishes, and to look in a different direction, you need to turn it, and it can take a while. It can take like 5 minutes to scan around and get a good volume, and that's not even a full dome, right? Because we only go up to a certain height, so we kind of get this strip coming out. Phased array is possibly going to change that in that it doesn't need to necessarily be steered around, because you can have it stationary, this flat array of emitters, and just by changing how you emit the pulse, the pulse can go out in a different direction. So if you look at the diagram on the top right, the analogy I'd use to describe this is that if you had a series of stones in a lake lined up in a line and you drop them, you know, along each other in sequence, what would happen is each one would emit a spherical wave, but then what you'd find is that because you did it in a sequence like that, that a more flat sort of wave would appear and go off in a different direction than the alignment of your initial stones. Hopefully that makes sense. So that's how you can steer the beam electronically. I've actually been inside this one that's photographed in the bottom. It's quite cool. So this has been used in military for many decades, but now it's sort of coming down into the academic domain and it's being used for other ways. There's some problems still to fix with it, but the potential is quite high. So you could scan sort of 360 instantly, theoretically. You could focus some of these beams on one thing and then different things as well. So I've got another video as well, which shows this off better than I can describe it. And I'll just talk over it. So yeah, this a lot of work is happening in Oklahoma with this. And yeah, so it came originally from the military and it's trickling down into academic research now. But you can see here this example of you could scan a beam in many different directions. You could also, for example, do a subset of scans on a tornado while simultaneously scanning something else in the sky like aircraft, and do it at much higher resolution and, as you can see here, higher frequency. So this is a tornado, this is Doppler velocity, and you just see there's more detail in there. And they're also planning to use this to essentially, before we'd have a set of radar systems for aircraft and a set of radar systems for weather. But they're saying, yeah, another advantage here of phased array is the ability to combine different. So you could combine budgets essentially, and buy a more expensive radar because you're getting it from 2 different places. So very exciting. So then finally, just 2 examples of new applications of radar. So when I showed you these different sort of colorful charts that show you different precipitation types or objects in the atmosphere, you may have noticed there's clutter and biological at the bottom. This biological one, it's very similar actually to World War II, where they were trying to detect aircraft and they were like a bit annoyed by all these blobs that were actually precipitation. And then someone eventually came along and said, actually, that's useful. We've been throwing away all this clutter and like what we think are insects getting in the way when we're trying to get rainfall. So we try and throw that out and discard it. And actually, it's useful to biologists. So there's a project at Leeds called BioGRAPHY, where they're trying to use dual-polar information and essentially create these kind of diagrams where you can tell different precipitation types, but for different insects or birds. So that could be extremely useful. And this is just kind of the cycle they're going through, where they've got insects that they can model in software, make some observations, and actually catch insects and find out what was there whilst observing it with a radar, and loop back around and gradually improve this and yeah, try and get a biological classification algorithm at the end. That's the eventual goal. So that's quite cool. So then finally, weather forecasts have been run on computer models for many decades now. It's the primary way we do forecasting. It started off with extremely low resolution, so 300 kilometers back in the 60s, twice a day, and you could get pressure from this, but yeah, you wouldn't really trust it to get like precipitation or anything else. Then in the 80s, that obviously improved and became more global as well, not just one region. And now the current state of affairs is that we have for example, a regional model which is about to be upgraded again actually, but the current state is 1.5 kilometer resolution. That's about to improve by a factor of 10. So basically, the model forecast is approaching the kind of scales that radars are observing on. And so people are trying to use radar to influence the starting conditions of the model. And this is through data assimilation. And the key thing here, which I don't understand the maths enough to give you a full lecture on, is that you don't actually get your radar observations, precipitation, and then put that into the model. What you actually do is you get the previous forecast and you ask the previous forecast model to produce what would be the radar image, or in fact, the actual reflectivity or ZDR, KDB. And then you provide the observations that you've made from your radar. You don't have to turn it into anything the model can see, just because the model has now turned into radar. And then it does some like statistical nudging and cost functions and stuff to minimize the multi-dimensional distance, I suppose, between the observations and the model. So yeah, I thought that was pretty cool. But yeah, that's data assimilation. So radars are going to be used more for data assimilation going forward. They're already used. The winds are already used, and yeah, lots of work is going on to get other variables and dual pole variables assimilated into a model as well. So wrapping that all up, that is. I'm going to come back to this wave and use that as a nice little timeline for us. So we had in the first 100 years the development of radar, of radio itself, and then it was applied to meteorology in the form of radar. And we recently just had an upgrade in the UK and around the world as well, actually, if you look on a decadal sort of scale. And now we're looking forward to all these upcoming things, especially in the research sense, coming into operational use, all these new technologies. And so that's why I think we're in the golden age of weather radar. And that's all I have. So yeah, please ask as many questions as you want, anything you want to know about radar in the chat, and I will wrap up there. Thanks, Rob.
More questions, because we didn't get very many questions come up. I can see the chat's going a bit wild now, so I'll leave Simon to mark them as questions while I ask the questions. This is good news for you that we're getting the questions now, Ben, because otherwise you were going to get my awful ones. But I will ask my first awful one, because the radar nerds might as well get out there to start with. So you sort of picked up the world of phased array radar, and I'll admit my own feeling is it's probably not. My gut feeling's always been it's not going to be quite what it's sometimes sold as, and I think a lot of the problem is that the dual pole, a lot of it seems to basically be artifacts. I'm not even convinced there are ways around. A lot of them seem an inevitability of the wave combinations. So do you have any thought? I mean, I can see it be really useful, but I don't think it will. My feeling is it won't replace old school rotating radars so much as be another extra tool. And I think that, as you said, the rapid updates and so on, brilliant. And I think they will be brilliant. But I'm not convinced it can do everything. For instance, the hydrometeor classification, it's potentially really important too.
Yeah, it's a good point. I mean, that video that I showed you was from, I think it was around 2010. You can kind of tell from the quality. I suppose it's a bit like the advent of fusion power, in that it's always decades, it's always 1 decade away, right? And then you have to get another decade. Oh yeah, it's just another decade. You have to wait. Yeah, you're right. There are problems. From what I understand from being a commentist, I think it's mainly like biases that you get, especially when you tilt. So it seems to be fairly okay from memory. It seems to be fairly okay in if you use it just pointing straight forward. But it's when you ask it to steer electronically that you get these sort of drifts in the dual pole variables, right?
Yeah, that's my understanding too.
Yeah, I don't know specifically what needs to be done to fix that, whether it's like a hardware thing that they're just waiting for, a piece of technology.
I've even seen suggested a phased array that rotates so that you can keep the square on to keep your dual pole, but you can look off to the sides rapidly for non-dual pole as a solution, and maybe that would work.
Yeah, I think isn't there a mobile fan kind of type radar? It's like a scissor lift that goes up on the back of these trucks, and then it's a tall board, and so they use the effect of being able to look in many directions at once, and they essentially fan out and look. They do the vertical with just with stationary, and then they turn it, so they sweep out the whole sort of volume a bit quicker.
Yeah, the same kind of idea.
Yeah, I mean, you could do like cone shapes or like domes maybe. There's probably tons of things to do. I tend to believe.
I think this is what we're saying, that we're probably a decade or two away from really the full potential of it, if not more.
Yeah, I'm just seeing this thing in the chat, so I'm going to hold this a bit. Yeah, I think I tend to think generally with technology is that. I tend to believe that it will get there. I don't really have any doubts that it wouldn't, because you could say that the dual pole variables were originally developed in the 1960s, or some of them, and you could say if we were then in the 70s, you could say, oh, it's never going to work, it's never going to get into operational use, it's too expensive or whatever. And I feel like, because that's a decade later, I feel like we're about a decade later in the research sense. So yeah, I tend to generally believe that technology will just continue improving. I don't really see any limit to it. So yeah, I'm hopeful that it will occur. And I know in the UK, I don't know what exactly the format will be, whether it's turning or not, but I'm fairly certain that the next upgrade the UK sees will be to phased array.
Yeah, very interesting. Right, so let's go on to other people's questions. So I'm going to hit the answer live and try and read them and then kill them off. So the first one is going to look strange, but I know how it refers. So it was Anthony with snow negative KDP.
Yeah, I saw that when it was coming up.
I thought you would have done, because I knew you'd looking out for that one.
Yeah.
So, shall I ask it in a more complete way, or do you want to answer it in a more complete way? Because you know how it refers.
So I presume what Anthony's saying here is that it doesn't believe that snow can have negative KDP in saying that the snow can't be taller than it is wide. I guess this is fairly anecdotal when I was creating these plots at the beginning of my PhD, but I I'm pretty sure at the time I'd seen something which says you can have only very slightly, but you can have this effect where the aggregates will be slightly taller than they are wide. I don't have anything extra to say really on that. Yeah, unfortunately.
I think it would strike me as surprising, sort of dynamically, of things falling, but I suppose for a short period, particularly if they're rocking or canting, maybe it's possible.
Well, when you think of Graupool in the conical shape, it does prefer this kind of vertical orientation, yeah, to a point. But I mean, the image that I showed in the slides, it wasn't altered, and that is slightly taller than it is wide. I think it's a laboratory experiment. But you can kind of imagine how it would happen. It's, you know, with snowflakes being so delicate and falling kind of slowly, they just sort of collect on the ends. And it's not like Graupool where it has like a, I mean, it does have a flow around it, but it's not as extreme. So you can imagine how they would sort of just come to rest on each other if two flakes of a similar size, moving at a similar speed, just sort of touched. So, but yeah, ice is weird anyway when you look at it from a radar perspective. So I think it's only very slightly negative, but thank you, Anthony.
Right, so the next one is by Richard, and I'm going to happily sit and let you answer the questions, because we had similar with Alex a couple of months ago. But this one, sometimes online rainfall radar images appear to show precipitation falling over an area, but none is seen on the observer on the ground. Apart from those occasions where the precipitation evaporates prior to reaching the ground, are there any other reasons why this happens? And to add to Richard, this happened to me today. Right over my head, radar said it was raining. My other half had gone out for a run and did not get wet.
It's interesting that this question has been asked, actually, because normally what people say is the opposite. They say that it was drizzling, it was very light rainfall, and the radar didn't show anything. So either way, the Met Office can't win, right? They're trying to strike a balance here between being oversensitive, because they're going to see clouds and the droplets within clouds in any case. And whether that actually results in precipitation reaching the surface or not is dependent mostly upon things going on below the radar beam, or just other effects that the radar isn't going to give you enough precision to see. So yeah, if they overdid the sensitivity and said, oh, okay, we're getting this much energy back, that must be precipitation in the ground, then you'd get more of this where it says precipitation and there wasn't any. But if they scale it back, then you're going to get cases where it was drizzling, and which is usually the criticism that the Met Office receives. So yeah, you can never really win. You've got to get some kind of balance. And there's going to be a variety of atmospheric conditions that have the same power coming back on the radar, and that could be precipitation ground or not. So yeah, it's very, I wouldn't say, it's not anecdotally chosen, but over time, they've realized that to get equal numbers of false alarms and misses, you know, they're going to have to be somewhere in the middle of that sensitivity.
I think part of the problem with Richard's, the sort of reverse of Richard's example, the radar says it's not raining and it's drizzling out there, is often that sort of drizzle can often occur in the bottom couple of 100 meters and the radar beams above it.
Yeah, especially over hills as well, where you get the cedar feed effect. So precipitation can fall through cloud in the mountains and become larger and be heavier. So you even more think, why did the radar see this? And that would be a case of the radars aren't very good in the mountains. The beams would be even higher because they're being blocked by the mountains below. I will say one other thing though as well, which you may have seen if you follow the Met Office on Twitter. You can get these cases where insects show up on the radar, and they're trying to be removed by the software at the Met Office. But sometimes there's such a strong signal that the software is just like, oh, okay, this must be precipitation. And it looks kind of weird, but yeah, sometimes that happens, and you see these.
Radars are very good at, they're very good at spotting flying ant.
Yeah, I was going to say flying ant is usually the trigger, and yeah, I don't know too much about it, but whether that's actually a real phenomenon that occur, you know, all synchronized on one day sort of thing.
Right. So the next question is, if biodar is helpful, which we kind of know it is, there's sort of insects and birds and so on, then is chemdar or chemical radar possible? Chemicals or aerosols forming clumps in mid-level, potentially weather altering, and could be concentrated or in weather systems, etc. So could you make a chemdar?
You could, but the problem is it's going back to these regimes that you can observe in. So you need the frequency of your system to be observing things. For what you want to observe, it needs to be the right ratio of wavelength to the object. And aerosols are so tiny that you need an extremely high frequency system, and then you get into a different part of the electromagnetic spectrum. So you'd be working with LiDARs. And there's some extra things going on physically with like the size of your beam as well with LiDARs, so that it's such high frequency. You essentially get like, it's a laser. So you get like a tiny like beam coming out of a LiDAR. And so you can detect aerosols with it. But in order to scan and get like a 3D picture of the atmosphere, it will probably take you hundreds of years, right? Because you're only getting a teeny tiny line as you're going around. So if you had, you know, you can imagine having, the hardware itself is so huge as well, and so much power and heat dissipation. But if you could stack many next to each other and create like a fan, like we were saying before, you could maybe do that. But it'd be extremely expensive. So that's the prohibiting factor for something like ChemDAR. I mean, traditionally, you just point a LiDAR straight up and wait for things to pass over it. And that is done, and it is useful. But yeah, you wouldn't get a 3D image kind of thing with it.
Yeah. I'm going to quickly flash this one up, but I know you actually already answered it, which was thank you, Ben. Could you show the book again? Show the book again.
I'll read it out for anyone who.
I was going to say I'll put it in the chat in a minute, because we've recommended this book to 2 master's students.
It's a good book.
Today.
Yeah, Radar Meteorology.
It's an excellent book.
Radar Meteorology: Principle and Practice by Frederick Fabry, 2015. So it's got a lot of recent material. Very good book.
Yeah, I'll write out those as well in the chat in a minute while you answer the next one. So Jack Hopkins, well, what have we got? So will recent upgrades offer much real-time hydrological, or much for the real-time hydrological uses?
Possibly. Trying to think through the processes. I mean, for my PhD work, one of the things that I considered, and I don't know if it's implemented or not, you'd have to ask the hydrologists, is if you know the precipitation type now, because you've got this dual pol information and these algorithms, you could, for example, have a very good idea of like how much snow is accumulated on a mountain. And then when you know later on that it's raining at that location, you'd have a good idea of the volume of liquid that's stored, or volume of water that's stored on those mountains. Whereas I think normally you just have to have like a really specialist sensor, or people measuring the depth of the snow and assume something about the density to try and get that information. So I can see that being one cool, added thing that we could get. I guess it's not really real time. Yeah, I don't know what. Someone would have to tell me what the hydrological community really wants the most. But I mean, okay. So one thing we can do is the KDP stuff with the amazing graphic of attenuation that Rob very kindly put out there in public domain. Using that variable, that KDP variable, can result in a lot more accurate rainfall rates than just using the reflectivity factor. So I know the Met Office now are using this KDP, this specific differential phase, for doing rain rate when the rain rates are very high, because previously when the rain rates are very high, the radar's not that accurate getting the amount, and that can be quite critical. And you'll see that the Met Office chart, the color bar only goes up to 32 mil an hour. So in really severe storms, it's it can be a problem. But yeah, the fact that we got dual pol now and KDP, that's a better way to get rainfall rates when we've got severe storms. So.
Yeah, to some extent, Ben, I kind of feel like I probably should have answered that question more than you did.
Yeah.
Really, in recent years, it's been the heavy rain from the radar, and I think the real answer is it's really only the last decade or so where hydrologists have really even considered radar as something they can use.
Mm-hmm.
So, and recent projects that I've been involved in have sort of shown that the radar can at least give you better information, because at least you can locate where the rain's falling within your hydrological model and so on. So I think really it's actually using radar is probably the biggest gain to be made at the moment, using radar at all. And then radar does have a bit of an issue in that it's probably least reliable when you most need it in the really heavy rain. So that is a problem, that it is stuff that's being worked on, and trying to get that into hydrological models and so on is happening.
Yeah. So would you say then that hydrologists typically would only use rain gauges at the surface? That's all they would trust?
Certainly what they have used in the past.
Because
we're slowly getting there. We're winning the battle.
Yeah, because I know Chandrasekhar said at one comments that they were doing some study in Texas, and it's now flipped. The sort of trust and belief in the observation system has gotten to the point now where the radar is being used as evidence to question that the rain gauge is functioning correctly. And that
I wish one of our MSc project students was in right now to hear that, because I think that synergy is where it's at for those two instruments as the solution.
Definitely.
Right, next question, which is from Alex. So a non-scientific question, but would you like to see something like radar scope? So that's what they had, the American thing that you showed us in the UK. So I imagine the Met Office are reluctant to do such a thing for some of the many reasons you've measured, but do you think we should have it? I know even more reasons why, but
yeah, I guess it needs to be.
I suspect you and I will give the same answer to this.
Yeah, it needs to be a bit. What's the word? Not political, but like sensitive about the answer I give here. Yeah, so radar scope, for anyone who doesn't know, it's this app that I was describing. Because in the US, they have a law that anything publicly funded has to be, like anything that creates data, has to be publicly disseminated. So you can get the radar files directly, like as soon as they're observed in the US. So this app was designed, I used to flick through all the raw data, individual radars. In the UK, we just have this, for the public, we just have, the gridded product at 5 minutes. Sure, it would be great to have something like that in the UK. When I was a student, obviously I had a bit more access to some other data, and it was cool to be able to see different processes going on in the atmosphere, especially the winds were quite nice. But it probably isn't going to happen. We don't have the same laws in the US about openly giving out data, and this is very valuable data, especially to the aviation industry. And you can argue that the Met Office is a public body and should do this because it was given the money from the government to do this, and taxpayer money, but they do actually have to pay that money back to the government, or as much of it as they can, by selling.
And it's not entirely Met Office.
Yeah, by selling.
The Environment Agency are heavily involved as well.
Yeah, so they do, they make money off off this data, and that goes back to paying on, because it was millions of pounds to upgrade this network. Some of that needs to be paid back by selling products, and if it was all publicly disseminated, then they wouldn't be able to do that. So there's pros and cons. Obviously, in America, a lot of commercial activity comes from making it public, like this app and other innovations. So yeah, it's a debate it's more of a government debate, I think, really, than a science.
I think the answer you and I would both give is it would be lovely to have, and I don't see it happening in the near future.
Pretty much, yeah.
Yeah.
Yeah, Simon's comment about making it an app and then putting a price on it. There's development time that would need to go into that. So would that just cancel each other out then, the development cost versus the price of the app? And you wouldn't get as many people in the UK paying for that, because from my experience, the main use in the US is for storm chasing, which you can't really do on UK roads as easily. So yeah, it's an economies thing and a government thing.
Anthony might remember the number. So if you do, Anthony, write in the chat. But there used to be a case that the most visited page on the Met Office app was the radar output. So radar certainly gets used. The sort of radar composites get used a lot in the UK, and people use them. I mean, obviously, I'm bound to use it a lot. I judge whether I go for a walk at lunchtime during lockdown or not, or wait until the evening by looking at the radar before I leave at lunchtime. But do you think? I think it would have a market for people to look at all the time, but as you say, there's going to be such a big development time and cost on that. Probably that might be too much to be worth looking into. Basically. Yeah, maybe
Simon, if you want to learn iOS and Android app development, you can pose your free development time to the Met Office. Then maybe it will happen. Yeah.
There you go. So Danny has agreed that he visits the radar page most, and I think it certainly used to be the most visited, and I'm sure that was the best part of 10 years ago. I first heard that there were a large amount. So I'm sure it probably is still one of the most commonly visited things, because lots of people I know that aren't meteorologists go and look at the radar output. They don't even necessarily know that's what it is, but they go and look at where the rain is at the moment to decide all sorts of things. Do they go out for a walk? Do they put the washing out, etc.? So with that, I think that's the last of the questions. In which case, I shall start drawing to a close. Firstly, let's all thank Ben. This is the most awkward point of using a Demio, where I can't hear everyone else clap, so I have to do a single-handed clap that counts for everyone. So I'll do a multiple round of applause. Each finger can be a separate clapping person.
Thank you. Yeah, thanks,
so
everyone.
thank you for an excellent chat, Ben, and I enjoyed the Q&A session.
Yeah.
I got too much of the radar geeks in, so well, thanks for that. Hopefully everyone else, you can see lots of virtual claps going on, so
that's great.
That's nice. I should so thank you, Ben. I just go through the quick last minute extras. Remember to keep in touch. This will appear on YouTube in a day or two, as well, on the Royal Metsoc YouTube account. And Helen left, and hope, but as it will come up with captions for your subtitles, so hopefully that will appear. And remember, it will sit in the archived events. There's an upcoming talk on the 12th for a virtual meeting on health and climate change, the health emergency. And currently, unfortunately, we don't have the next Southeast area meeting to announce what it will be. So keep your eye on various social medias and the Metsoc website, and we will tell you when the next one is as soon as we can. Anybody got any good ideas for a Southeast area speaker you'd like to have? And perhaps this is an extra good time during virtual meetings, because we don't have to worry on virtual meetings about trying to get somebody to the southeast. Then please, yeah. And Ben is advertising your Yorkshire Centre. Ben, if you want to turn your video back on, you can do an advert for your Yorkshire Centre meeting now. While during my last slide.
Yeah, I'm actually part of the Yorkshire Local Centre Committee. Unfortunately, I don't actually know too much about this particular talk. I've been hosting quite a few recently, but don't know too much about this one. But Alexis Percival is a very good speaker, so I'm expecting good things. And yeah, you can register online the same as you did for this talk. It's only what, 8 days away? Yeah. So thanks.
Excellent. Brilliant. Thank you, Ben. And with that, I think I shall end the meeting, and I'll close it off in 30 seconds to a minute. Enough time for everybody to say goodbye. But goodbye, everybody. Thank you. Hope you've had a good evening.